Greetings, folks. Welcome. The practice of statistical inference involves using information from a sample to say something about a population. A common application of statistical inference is estimating a population proportion. So an example of this might be, you might want to estimate the percentage of all Americans who would select Todd Gabe for president. Unfortunately, it would take forever to ask every single American whether or not they'd vote for Todd Gabe for president. So instead, we collect information from a sample and we do inference to try to estimate the percentage of all Americans that might vote for me for president. When we estimate a population proportion, we calculate a sample proportion or percentage and then put a margin of error around it. Here you see the formula. You have an uppercase P on the left-hand side. It represents the population proportion. And that population proportion is equal to a lowercase p, which is a sample proportion, plus or minus a margin of error. So an example of what this would look like is you could say 52% of Americans would select Todd Gabe for president, plus or minus 4%, and that 4% is the margin of error. There are two factors that determine the margin of error. One is a confidence level, and that's something that you set as the researcher, and the second part is the standard error of the sampling distribution. Here you see the formula for the margin of error. The first part is a z-score, and that's based on the confidence level that you set, which I'll show you what that means in a second. But the notation is z subscript alpha divided by 2. And then the second part is the standard error of the sampling distribution. That's the square root of the percentage, or the proportion you get from the sample, times 1 minus the proportion divided by n, which is a sample size. As a researcher, you set the confidence level for the confidence interval that you're going to estimate. So for instance, a 99% confidence level means that you are 99% certain that the confidence interval that you calculate will include the true population proportion. A 90% confidence level means that you're 90% certain that the interval that you calculate will include the true population proportion. So if you want to be more certain, you actually need a larger interval. Here are the steps that you follow to find the z-score that you'll use to calculate the margin of error based on the confidence level that you set. The first part is you set the confidence level, so that could be a 99, 95, 90, whatever you want to set as a researcher. So you have that confidence level, then you take 1 minus that confidence level, and that gives you alpha. So let's say you're doing a 95% confidence interval, 1 minus 95% gives you an alpha of 5%. Then you calculate alpha divided by 2. So if alpha is 5%, then alpha divided by 2 is 2.5%. Then you find the z-score that corresponds with that alpha divided by 2. So let's say you want to estimate that 95% confidence level. Your alpha is 0.5. Alpha divided by 2 is 0.025. And then again, you find the z-score that corresponds with 2.5% of the distribution. Here's a standard normal distribution. You see it's symmetric, single-peaked, and bell-shaped. And you see that it's centered around 0. I drew what would be about 2.5% in the upper tail and 2.5% in the lower tail. So that 95% in the middle is the confidence interval that you estimate. Of course, I put question marks because we don't know yet the z-scores that correspond with the top 2.5% and bottom 2.5% of the distribution. When we go to look for the z-score that corresponds with the top 2.5% of the distribution, bear in mind that the standard normal table gives you a cumulative probability. So we'll really be looking for 97.5% of the distribution. Because again, with the cumulative, we're saying 97.5% of the distribution is below that point, 2.5% is above it. So here's a standard normal table. Again, it shows the cumulative percentage of the distribution up to that z-score. So down the first column, you see z-scores 1.5, 1.6, 1.7, etc. And we're looking for 97.5% of the distribution because, again, it's a cumulative value. So that's really giving you the upper 2.5% of the curve. And you can actually find the value, 0.975. That corresponds with a z-score of 1.96. Now, if you're looking for some extra practice, you can also look for the z-score that corresponds with the lower 2.5% of the distribution. So here, if you look at the standard normal table, you find minus 2.5, minus 2.4, minus 2.3, etc. in that first column. So now we can actually look directly for the 2.5% because, again, it's a cumulative value. And sure enough, you find that 2.5% of the distribution corresponds with a z-score of minus 1.96. Of course, we already sort of knew that because the standard normal distribution is symmetric. So if 1.96 corresponds with the top 2.5% of the distribution, then minus 1.96 will correspond with the bottom 2.5% of the distribution. So now we can go back to our standard normal curve and actually fill in these values. So where we had question marks before, I put in a 1.96 and a minus 1.96. Now we'll go back to the formula for the confidence interval. You have an uppercase P on the left-hand side. It represents the population proportion. That's what you're trying to estimate. Equals P, which is the sample proportion. That's something you can calculate and go out and collect some data and calculate that proportion. Plus or minus 1.96. That's the value of Z that you use for a 95% confidence interval, because 1.96 corresponds with the top 2.5% of the distribution and the bottom 2.5% of the distribution. Then you see the standard error of the sampling distribution, which is the square root of P times 1 minus P. Again, those are proportions. So those are things you can calculate with the data that you collect. Divided by the sample size, which is something you know because you're the one that's collecting the sample, so you know how many observations you collect. In a different video, we'll actually take this example one step farther and put some values in there so we can actually give a precise confidence interval.